And one thing I would like to say is 여러분 안녕하세요. 이름이 Mike입니다. But I'm sorry I don't speak Korean. 단지 3일. But nice language. And it's so hot. Yeah. I'm really impressed by this country. When I arrived here, it was raining when I got to the city, and I crossed the road at Samsung station, and it was raining so much, and I hid under the transformer, and somebody in their car stopped, got out in the rain, and gave me an umbrella. Amazing. Then I got to my room, and my door spoke to me. Amazing. And not only that, a sexy voice. Yeah, I think I got the hots from my door. Fingers crossed. So I'm going to give a talk about Keras, which is a Python framework for doing deep learning.
Now fixing this problem.
Okay, so I'll just talk while you're fixing the problem. That's okay. Okay, yeah, so I'd like to talk about Keras, which is a Python framework for deep learning, and you can do things like machine vision, and you can do understanding text. How many of you are using deep learning frameworks? Yes? Okay, great, so some of you. And what about machine learning in general? Okay, and Python programmers? You're all Python programmers, right? Cool. And okay, so more about me. I've been a Python programmer for like about the last 9 years, I think. And at the moment, for the last 4 years, I've been working for the United Nations. We have a project to it's the World Food Program, so we have a project which is Python-based, where we give people value that they can use to buy food. Got it? But I should say I'm not representing the UN at this talk. I think they still haven't, different input. Let's see. So my interest in machine learning is, well, I did my degree in a bachelor's degree in artificial intelligence, but that was a long time ago. I was really hoping when I did my degree that I could learn a lot about neural networks and things like that, but at that time we didn't really have the technology wasn't really up to scratch. So, but now, like in the last few years, a lot of things have happened, especially using GPUs, where we can suddenly do a lot of the cool stuff that had been dreamed about in that time. Okay. Yay! Great. 좋아요? Is right? Ikkyo 좋아요? Okay, so, right, I've done that bit. Okay, so the objective of this talk is, show you that you can use Keras to recognize objects in images. I was a bit ambitious when I thought about doing this talk with like, doing face recognition and stuff like that, but I'm just going to use the simplest examples. So I'm sorry if any of you have seen like MNIST digits, but that's what I'm going to use. So Keras, okay, I got into Keras by doing some tutorials, and what I noticed about the tutorials is that they always give you the perfect example when it doesn't go wrong. So, but when you start playing with something yourself, then you find that you're going to have problems. So I tried to like remember things that went wrong and how I fixed them. Okay, so you want to do some deep learning machine vision. You don't need a PhD. I spent so much time reading papers, and you don't. Yeah, it's good, but you don't get so far. You don't need to really understand really deep mathematics to do this. It's more about experimenting and trying out ideas and trying to like being okay to like take your time to solve a problem, read about it, ask people about it, and then you get a really good understanding of what's going on. But you will need a decent machine. I found this out pretty quickly. You definitely need a decent GPU. So I got like a 1080 GPU. This is pretty good one, especially with good memory bandwidth internally. So, and it should be a CUDA CPU. Well, ideally CUDA CPU because most of the frameworks are using CUDA. It's good to understand, well, you need to understand like SciPy, NumPy, especially like that it's passing around like these, you're dealing with big chunks of like arrays or multi-dimensional arrays of numbers. Okay. I'm not gonna go too deeply in the installation requirements. So there's just not really enough time. There's enough already in this talk. So yeah, it's not that difficult to do. Like each of the Theano, Tensorflow, and Keras will have their own installation instructions you can follow elsewhere. And recommending people use Jupyter. Do you use Jupyter? You know Jupyter notebooks? Really? Nobody knows Jupyter? You must. There must be someone. Yeah, Jupyter's cool. Like, so Jupyter is great for this style of work because you can, well, I'll show you, but it's like you have a notebook and you can like try things out, and it's good for experimenting. And Matplotlib is great with that too because it allows you to visualize a lot of stuff. Okay, so briefly, do I need this slide? Like, what is deep learning? It's a branch of machine learning. Some people say it's like a rebranding of neural networks, maybe. But I think the difference is, okay, everything on this slide is basically neural networks, like that we've had for decades. So you've got the multiple layers, and they're doing nonlinear transformations, which is important. So you have a nonlinear function, like a sigmoid function. Okay, here's a rough idea. So you have here's your, if you imagine this is like a simplified idea of a brain cell where you have like, you're taking inputs from other cells, you're multiplying them by the weights of the connections, summing that up, and then putting that through a nonlinear function to get a result. And by doing this, you can get it to learn features. So yeah, going back, like, what is machine learning? For me, it's like you're finding a function. You have the inputs and the outputs, and you want to know what is the function that goes between them. So deep neural networks, like maybe you can say the characteristic is that you have many hidden layers. I've seen networks that have like 156 layers now. So that's kind of a distinction. The reason why that's new is because there are problems with training very big networks like that. So there's this old saying that neural networks are the second best way of doing just about anything, but that's cool because that's where the value comes from, because they're okay at doing everything, pretty much. Like you could, in fact, it's proven that with a simple network, you can three-layer network, you can learn any function. However, the caveat is that the middle layer can be arbitrarily large. So going back to like the deep neural networks, the idea is that each layer is building up abstractions, so you can be more sophisticated and have fewer nodes overall. Yeah, so you got some modern techniques like Dropout, which I'll cover later, regularization, did I cover that? Convolutional networks, I'll cover that. So Keras, I looked at Keras, I looked at Theano, I looked at Tensorflow, and then found Keras, and I like Keras because it's pretty minimalist. I like that kind of style. It lets you solve your problem without having to deal with too much extra complexity. There are some other talks about Theano and TensorFlow, and it's great to understand them. And if you're already using them, then Keras is, it depends what you're doing. Like Keras is simpler. You may have some features of those frameworks that you want to use, but Keras won't support them, but they tend to be specialist. It's got a nice abstraction level, so you can easily create your networks and connect them together. So it's quite beginner friendly. And it's MIT licensed. So you've got backends, Theano and TensorFlow. Do we understand what Theano and TensorFlow is? So these are frameworks for fast numerical computation. You describe a mathematical operation on your data, and then it will basically convert that into code that is going to run really fast somewhere, usually the GPU or maybe on the CPU. So I kind of see it like this, that Theano and TensorFlow are like more powerful and can be used to do more stuff. And they can certainly be used for deep learning, but they are more general. So it's kind of like having a multi-tool where you just want a spanner, or a screwdriver in this case. So that can make them a bit difficult to use. Oh, and the lead developer is Francois Chollet. I've started contributing a little bit. The good thing is because it abstracts away the backend, so you can write your program and not care about the backend. So if you found that you get better performance on TensorFlow than Theano, then you can just switch and you don't need to change your code, which is great. And it's all Python. You don't need to worry about like weird XML file formats like I think you have to do in Caffe and things like that. And then you've got it's nicely organized into sort of components that fit together. So you have different layers. So there's different types of neural network layers. So you've got the dense layers, which are the sort of classic ones, convolutional, which I'll show you. I'll explain some of these later. But basically the idea is that you've got all the pieces and you can put them together quite easily. It's modular. So try and do a demo. But what should we do? So there are these standard machine learning problems. And they're great to know because it allows you to compare different techniques. So when someone says, like we've improved 1% on this standard problem, and it's already been worked on for like 30 years, then that's a big deal. And some of them are used in competitions, and you can also use them to compare your ideas. And another very useful thing is they give you an idea of when to stop trying to improve. So if the state of the art is 96% accuracy and you think you can get 99%, then you can kind of give up at that point, or just like aim lower. So, like you're not going to achieve it easily. So here are some standard ones. So MNIST, which I'm going to use, very standard, is where people have drawn or written handwritten digits have to be recognized by a machine. There's also other ones where you classify different images by what they are, and yeah, but I'm not going to use those. That's kind of a boring slide. Another nice thing about Keras is it already knows about these data sets, so you can just load in your data from Keras without having to fudge around with other frameworks or anything like that. And it's always like you have inputs and outputs, and a lot of the time they'll be written in the code as X and Y, or X train and Y train. That's very common, or just because it's the mathematical, you know, you've got a function Y equals fx, so it's just a mathematical way of doing it. But I like to write it with the actual names of the things, so you know what you're dealing with. Okay, so this spelling mistake. Jupyter. So this is from a Jupyter notebook, and this is what you see where, actually, I can, if I've got a connection, no, I'll stick to the slides. Yeah, that's just showing that, like, once you've got everything installed, and you start, when you import Keras and it imports Theano, then you'll see it. You can check that it's using the GPU like this, which is kind of important. You want to be using the GPU because it's much, like, otherwise you'd be waiting too much. Okay, so when I started playing around with this stuff, one of the first pitfalls I fell into was just giving the network my data as is. So you'll find that, like, a general thing is you want to prepare your data for the network, and what that usually means is that you want to normalize it. So if I go ahead, like, here's, like, if this is an image, this is the first image from MNIST, which is an image of someone who's written an image of the number 5, and each pixel value is from 0 to 255. Whoops. Where are we? So, but what you want is for all of your values, well, you want to keep your values around 0, so between 0 and 1, or -1 to 1. So it's just a matter of dividing those values, which is really easy to do in NumPy. And you also might want to reshape your data. And for image work, I've found that, or it's fairly well known that you often want to, if you've got like an RGB image, that's maybe not the best way of representing your data for machine learning. So it's often useful to change it to HSV, because then you've got, like, one channel is just the color, and one channel is like the brightness, and actually most of the information is in the brightness, and the color might not be significant. In fact, sometimes you want to throw the color away, because maybe, like, if you're training on an image and it's like you're looking at cans, but it's all Coca-Cola cans and they're all red, then you might end up training the network to recognize red things instead of cans. Another thing to understand is one-hot encoding. Anyone heard of this? Okay, so one-hot encoding. So usually, like, okay, for image classification tasks, you're feeding an image into the network, and then you're training it to give the right outputs, and the output is a label. So for example, for MNIST, you've got 10 different digits, 0 to 9, and so how do you represent that at the output? And this is the normal way is using one-hot encoding. So what that means is like one value will just, there should be only one output on at the end, which represents the value you want. So 1 would be encoded as 1, 0, 0, 0, and 2 would be 0, 1, 0, 0. 3 would be 0, 0, 1, 0. Make sense? Maybe easier to see in the code. So, okay, here's some horrible code, like here. But so the idea is we're loading the data. Okay, so I'm showing the code that's leading through an example. This is actually runnable code. Like, if I got time, then we can run it at the end. So, load the data, prepare the data. So in this case, we're reshaping the data. And this is a standard example that I think you can find in the Keras code. So Keras comes with its own example code, which is great. I just reworked it a bit. So what we're doing here is we're taking that image, this image, and now it's a square, and we're going to flatten it out into just a line. Like so, we don't care about the spatial relationships of the pixels. We're just taking each pixel as is, and putting that through to a dense network. So this is the old way of doing things, and but this is just to explain the code. So, and then you see where it's divided. The image is divided by 255 there in the middle. My mouse doesn't work. So that's just the normalization. I think we can move on. Yeah, so here's another general tip is always try to visualize or inspect the intermediate data, because when you are creating these models, and you won't find this in the because in the tutorials everything works. Okay, in the tutorials everything works smoothly. So you're basically creating a long chain of computation. So anything going wrong in the middle is going to give you garbage at the end. And you can use PyPlot to visualize this kind of image data. So here's the model being made here. So this is the interesting bit. So what we're doing here. So Keras has two types of models. One is this sequential model, and that's like the simpler one. There's also like something called a functional API, where you can make big graphs of neural networks, which is more specialized. But the sequential model is just like one layer after another. So it's the same as I showed in like that slide back with the deep neural networks. So the API is so simple. You see, like we make a model and then we simply add layers, and the layers will stack on top of each other. And then each layer you can specify some parameters. So a dense layer is a layer where every cell is connected to everything else underneath it. And I'm using 28 by 28 there, so that's the image dimensions. But it turns out, it's just it's just a line of cells. You can think of it like that. The init parameter, that's how we initialize the weights. So we start off with some weights in our layer, which are going to be trained, but initialization is kind of important because you want to have some randomness in there so that they can start honing in on different features. They'll be more attuned to different features. And the activation is the function, the nonlinear function. This case, well, we don't worry about that. And then we compile the model. We need a loss function, and a loss function is a function which tells, when you're training, it'll tell you how far off you are from what you expected. Categorical cross entropy is one of them, but there are various others. And you need an optimizer, which is the algorithm that does the training, basically. I often ran into this issue where it would say that you've got mismatched dimensions. Because what happens is you're building layer upon layer, and the input from one layer has to have the right dimensions for the next layer, if that makes sense. So, and then if you don't match it up, then you get this awful error about mismatched dimensions. But Keras has this great thing called model.summary. So when you call this method model.summary, then it will describe your model to you. You can easily see what's actually happening in your model. So you can see each layer here and what the output shape is. So these are very simple, and they're just producing a single line. The first one has 784 neurons, and the second one is classification, so that's just 10. And the total params is interesting as well, because that gives you an idea of how big your network is, how long it will take to train. And some terminology is epochs. An epoch is one training session using all of the data in the training set. Batch is like you're dividing up the samples and training them together and updating your weights per batch. Then you've got validation data and training data, or training and test data. So training data is the data it will be trained on, and the test data will never be trained on, should never be trained on. It's just to see how well it's doing. Okay, so in Jupyter you run like this. We have this API model.fit. So you give it your training data and the training classes or labels, and the validation data and how many epochs, and you get back a history object. But it will. This is showing the accuracy improving as it's training the network. You see already in the first epoch that it's already up to like 96% accuracy. That's because it's already seen 60,000 digits. And then, if we skip forward, just in the middle there, you see model.predict. So that API, that's after you've trained your network. So then you want to use it to predict from other data. Okay, so here we go. We present it with this. In this code, we present it with two images, so it's learned what a 5 is and it learned what a 2 is. But down here I've put the probabilities that it had for different classes. So you see like the 5, there was a little bit that it thought it could be a 3 there. That makes sense. Okay, so good, not only in Keras, but a good thing for all machine learning is like having these nice accuracy plots, so you can see your accuracy going up with the number of epochs in this case, and that gives you a good idea of how well the network's working. So if you've had some cool idea of how to like train networks better, you can see it on these charts. You see here like the training images are much better accuracy than test images, and that's quite common. The idea is that you want to get the test image, like the test data scores as high as possible. And then there's a common pitfall called overfitting. So I've drawn an overfitting example there in red. So the training accuracy goes high. After a point, the training accuracy goes up and the testing accuracy goes down. And that's what's happening there, is that the network is is getting very specifically attuned to your training data. And the way to one way to fix that is adding dropout. So dropout randomly turns off bits of the network. So you can add a layer in Keras called a dropout layer, and that will turn off bits of the network. And what that does is it kind of randomizes things a bit, and it forces the cells that aren't turned off to, how to say, like to carry the responsibility of detecting features from the other cells. Okay, and also on these curves, you can get an idea of when to stop training, like when you've had enough. This can be important, you know, because like sometimes, and something I forgot to mention is there's a lot of hype about deep learning, but you soon realize that these networks, you may have to train them for hours or days or sometimes even weeks if they're big networks. So that can be a big cost if if your GPU is burning a lot of electricity. So it's kind of important to know when to stop training. Okay, so that was a very simple one. Now we're looking at convolutional layers. So in a convolutional layer, and this is like the cool new thing in the last few years, where a convolutional layer is, you can imagine it as kind of like it's the same network is looking at each point on an image and the surrounding area, and then the value it generates is then used to create another layer, and they will have different filters or feature maps, and those filters or feature maps are just going to be training to look for different features. And next slide. You need to combine these with pooling layers. So this is a pooling layer, and a pooling layer consolidates features from the layer above. So the idea is you detect features and then you consolidate them. And the reason why you want to do that is because, you know, if you're like looking for someone's head, and if they tilt their head or they got it to the side, it's going to cope with that. Because, well, you can see here it's like, this is a max pooling 2 by 2, so it's just taking the maximum of each of those squares to produce an output. You can see it will shrink down the size of the next layer. And what happens? What was I going to say? Yeah, so if those numbers represent features, then it's picking out the relevant features and ignoring things that it doesn't care about. Okay, so here's a convolutional example in Keras, and you can see it's done the same way. So we're just building up layers, and so you've got dropout layers there. You've got this is a standard example in Keras. You've got 2 convolution layers, and using that we can get a better accuracy. I should say, like, there's a guy called Andrew works at Coursera, and they did some studies over like a load of different, looking at a load of different research, and found that, you know, despite what people were thinking, that they had come up with better algorithms for training networks, a lot of the improvements could just be attributed to the increases of size of the networks, and like the more training you give them as well. So, but I think convolutional gives you the advantage. It's a real improvement because you've got far fewer parameters. If you think about a dense network, then you've got like n by n parameters. So you've got this huge number of parameters to train, and it doesn't really matter where where things are. It's like you're basically like training the network to recognize a cat in the top left corner or the top right corner. It's still the same task. So by having fewer parameters, it's quicker to train. Okay.
Excuse me.
Yes.
Can you show the recognition rate of the training and the validation? How the validation can be higher than the training? For example, in the bottom, the validation accuracy is higher. Is it because of the convolution and the mask?
All sorts of things can happen, and it's interesting. Which line do you see that?
Last line.
Last line. So
Yes,
the accuracy is 9861. Yeah. It can just be that it got lucky. You know, because there's a lot of randomness involved in this. I mean, you're initializing the weights randomly to begin with. So you can see like if commonly you'll see on a loss curve that it will go up quite sharply, but it's jittery all the way, and it can easily be that if the test accuracy and the training accuracy are close, then some randomness, you can get effects like this where you're surprised to see that the test data has a better accuracy than the training data, or it can be that you haven't got very good test data. Yeah. How are we doing for time? 1 minute. Okay. I'm just gonna. There was some. Yeah, there's too much to talk about. I'm just leave some further reading. I'll leave that up at the end. I want to whoops. I wanted to show you some weird loss curves, if I can, because that's cool. Oh, where is it? No. Okay. Right, it's going crazy. There. How do I get that? Okay, yeah, here we go. So I like this page. This is like Rogue's gallery of loss functions. So this is where like people have trained networks and then strange things have happened. So this is effects of dropout, but I like some what's going on here? It's like yeah, you'll see things like this where it maybe like goes up and down. Maybe like the training data is very easy at first. Like let's say you're looking for images and most of the images don't contain anything that you're looking for. So first thing it will learn is just to say there's nothing there. Yeah, so then you get very high accuracy, and if like 90% of if your training images are like that, then it'll be 90% right to begin with, and then it will start going down as it learns that actually like it has to look for certain things, but then you get some really crazy curves. Yeah, what on earth is going on there? But okay, this is just pretty pictures until you start thinking about them. I'll put the reading list up. Okay, so thanks very much for listening to me go on and on. And and yeah, do try it out. I mean, that's the main thing. Like, just I hope that you will try it out and don't be afraid. Yeah. Yeah.
Thank you for the speaking. Oh my God. 혹시 질문 있으신가요? 질문. If you have any question,
Yeah, I have a question. You talked about the
yes.
drop layers.
Dropout layers?
Any questions?
Oh, sorry. I didn't realize there were time for questions. Sure. Oh.
You show the slide.
Yeah.
혹시 죄송한데 질문 있으세요?
I share the slide.
예.
reduce the
나와서 좀 질문 있으시다고. 예. 어떤 질문?
질문하고 있습니다.
아, 예. 아, 죄송합니다. 아, 예, 죄송합니다. 제가 앞에만 너무 신경 써가지고. 예. 하세요, 예.
So, 먼저 영어로 말씀드리겠습니다. The speaker showed that there's an advantage to using dropout layers, right?
Yes, yes.
But in my opinion, it's hard to determine which node or which layer to drop out. So how do you determine which one to drop out?
Okay, this is a good question, and I would like to answer it generally, if I may. And the answer to a lot of these questions is you just have to experiment. You know, I'm sorry to say, but like I can't give you a straight answer because it will depend on the problem. Because if you're asking like where in a network to put a dropout layer, it kind of depends like what features like, because each layer, like each layer builds up like a higher abstraction of features that it's looking for. So for example, like the first layers in a convolutional network might be looking for just like edges, and then the second layer might be looking for like lines, and the third layer might be looking for curves and colored shapes and things like that. And you know, as you build up, you know, you're looking for like, you know, things like parts of faces, and you can go like amazingly high. Like you know, you can actually train these networks to like recognize things like happiness and friendship from like looking at images, because they can see, they can get that abstraction. So if you're like asking like where to put that dropout, it just depends like, I guess it depends like what feature that you care about that is too regular in your training data.
Okay, thank
Yeah.
you. And another question is you said that it takes hours, even days or weeks to
Yep.
train.
Yep.
So that means we need a lot of data to train. So how much data do we need to properly train the network?
I think that's a good question, because there's like a different kind of machine learning where we're trying to learn with very small sets of data. So in that case, you're trying to really be good at generalizing. So the more data, the better. But more important is that you've got representative data. So you know, if you are training something to recognize faces, but you only train it to recognize faces of people in their 20s, it might have trouble recognizing children's faces or older people's faces. Yeah, does that make sense?
Thank you.
Yes.
If I'm interested in a one-dimensional time series data, then if I want to just imitate your earlier model by the convolution 2D into convolution 1D and the max pooling in 2D and max pooling 1, is that approach is the better, or do I use the recurrent neural network? Which one is the better? Sequential model with the convolution 1D, max pooling 1D, or recurrent for the one-dimensional time series?
Okay, so you're asking which to use the convolutional layers or recurrent layers for a 1D time series. So if it's a time series, you know, it depends on the problem. Like if and it depends like kind of how you present it to the network. So recurrent networks are useful for, well, basically like storing some state so you can remember what's happened before, right? But convolutional networks have also been used successfully to look at time series data, and Keras does support like a convolution 1D. I should say I haven't played around too much with the recurrent networks.
If you look at the detail of the recurrent neural network, the convolution in a 1D is approximately similar to the autoregression. The time-related input in a recurrent is similar to the convolution.
Well, I don't think so, because in these, like in the if you're just talking about the convolutional networks that I've shown here, then it's just like a feed forward, always feed forward. So you don't have any going back. So you don't have like a time delay, right? And you could I guess you could kind of simulate it by having the data fed back in or something like that. Again, I think it just depends on the problem. Does that help? Any more questions? Or we really have to go? It's finished?
Yes, to finish.
Okay. Well, 감사합니다.